good morning and good afternoon to the people who are attending this session. We're going to be spending the next 45, 50 minutes talking about low flow, high head pump applications and reliable solutions for these type of pumping applications. And we'll have an opportunity for questions later on. So please, if something comes up, try to remember those or jot them down, and we'll have a period at the end where we can address your questions at that time. Just a brief introduction. My name is Steve Osborne. I'm the product director for Trillium Pumps USA, one of the companies of the Trillium Flow Technologies group. I've been with the company for almost 40 years. And so I have an engineering degree from the University of Oklahoma. I will be joined today by Sam Eccles. Sam has an engineering background with over 15 years of industry experience, and he currently serves as the product director for all of Trillium Flow Technologies, and he has experience in both quality and product management roles, as well as a strong engineering background with a mechanical engineering degree and MBA. And you'll get a chance to hear from Sam also today, and it's be a real treat.
Perfect. Thanks for the introduction, Steve. So just to give a very, very quick recap of where our key sites are across Trillium Flow Technologies. We're essentially made up of three key divisions. So there's the pump side, we have the turbine brand, which is covered by one single heritage brand in Allen steam turbines, and the various valve brands that you can see in the green section there. Not gonna talk to this slide too much, just want to give a very quick overview of focusing in on the pump side and where the key sites are. Again, I'm not going to talk to every service center, just to highlight that the majority of our OE manufacturing capability is split across the sites in Fresno, California, Milan and La Spezia, and the last two both in Italy. And we have significant service centers in Houston, Bedford and Aberdeen. And then just as a very quick overview, again, I'm not going to go through the whole history. As you can see it there, it's available on our website. And I recognize it's not what people joined for, but just to give some idea of, we recognize the Trillium name is quite new. We just celebrated our 3rd anniversary just this week. But we just want to highlight to everyone that the brands that make up Trillium and the heritage behind it does go back to 1828. And particularly for this webinar, the pump brands that are most relevant with the Gabionetta and Termo Mechanica, you can see were founded in 1897, 1912. And then where the Roto-Jet heritage, we can trace that one back as far as the 60s as well, as we'll talk through. Again, just to give a very brief overview of the whole product portfolio, we talk about quite a lot of different pump types in this webinar, because this kind of flow pattern that we talk about is very, very, very specific, but it does cut across several of these pump types. You can have overhung selections, you can have between bearing selections, and there are some vertical selections that we're not going to touch on today. But what we wanted to just highlight is we do have a full range of these, and we think it puts us in quite a unique position to advise on best selections for these low flow, high head applications. But we will also want to be transparent that we don't believe there's any pump vendor that has absolutely every type of pump for these kind of duty conditions. And we're highlighting off the bat that we do not have the OH6. We are still going to talk about that product. It is a very, very unique solution, and it absolutely has its place in the industry. And we just want to highlight that some of the times that these units are selected may not always be optimal. And we're also going to highlight the times when some of our more conventional products wouldn't be optimal for these duties. And you can see the markets that we cover. They are largely as you expect for a global pump company. They do a huge amount in oil and gas, water and wastewater, as well as supporting the power and general industry markets. And then I'll hand back to Steve to just run through and set up the rest of the webinar around some of the main challenges with these low flow, high head applications.
Well, thank you, Sam. When we look at the low flow, high head application, then it's probably best to take just a minute to understand what are the applications we're referring to. In general, we're talking about heads, applications that are below 100 cubic meters per hour or 440 gallons per minute, and above the 150 meters of head. So there's really no one-stop shop that's going to give you every one of the solutions that you might want to use there, but there's a variety of pumps that are applied in different services and that would fit in these parameters, whether it's an OH2 or a between bearing design, positive displacement reciprocating pump, or the pitot tube pump is what we're going to have most of our focus on this morning. The value is a lot of times these are relatively low cost solutions because the flows are low, and we're talking about some machines that may not be typically very expensive, but there can be tremendous operating costs and tremendous downside if the pumps are not selected carefully and correctly. And of course, one of the real obstacles with any time we're selecting a pump is making sure that we're specifying a pump that actually is going to be operating at the duty point. And of course, we're all aware that frequently there's margin that's added on top of margin, and we wind up with pumps operating that are way off the best efficiency point of a pump. And those are the kind of situations that we typically want to try to avoid. And because when we are operating away from the best efficiency point of a pump, then that's when we tend to suffer high rates of bearing and seal failures because of the recirculation that can occur in a pump. And we'll touch on that a little bit as we go through the presentation.
Okay, perfect. And with that, we mentioned at the start when we had the API chart with all the different designations, just some of the different options that are available. So the most common application when we think of kind of low flow standard applications, relatively sort of low to medium head, would be an OH2. And single stage, radially split, overhung pump, near center line mounted, the most common pump on a refinery. These can make 70 to 80% of those units. And they are very commonly used on these duty conditions. The challenges that you get into with this type of pump, particularly for the envelope that Steve was just talking us through, is really the head limitation. Once you're getting over sort of 150 meters of head, these pumps just aren't suitable anymore. You start pushing impeller diameter, you start running at 2-pole, whether 50 or 60 hertz, and you do run into vibration issues, you run into shaft deflection issues on these units, and they just cannot reach the upper head limits that applications require. So they also aren't very good for the very, very low flow services, as we'll talk about in a bit more detail around the multi-stage units. But still, they have their place, they have their time, they are a very robust, reliable. There's a reason they are the most common pumps on refineries. And the footprint compared to everything else we're going to talk about is a medium size. What's come about in relatively recent, over the past decade or so, is a much more popular and more customer willingness to move to what we would call a very low flow OH2 pump type. This is very similar to the OH2 that we've just shown. They will offer shared back plates and bearing housings, but everything else in front of that is different. It's typically a Barsky designed impeller, which allows for these ultra low flow, high head conditions. Now, as with anything in engineering, you don't get something for free. And what that does trade off is efficiency. So the efficiency on these units are very, very poor. You're often talking single digit. And now what we wouldn't state is that these do have their place. And when you look at them on an individual basis, because they are relatively low power machines, sometimes that efficiency is overlooked and almost ignored. But when that's looked at a whole across all these services on a refinery, because these units can be so common, it can add up, it can become significant. They also, again, they're very much a middle of the road design in terms of some of the features and benefits we'll talk about on the other products. They are reasonably flexible in terms of operating window. So they have a wider operating range than a pump with an inducer would, but they don't have as wide a range as some of the other options that we'll talk about later. And again, the footprint's pretty much identical to what you would find with a conventional OH2. And then finally from me, we'll just talk to probably the most expensive solution. And that's to go with the kind of multi-stage units that you see here. So on the top, you're seeing an axially split BB3 design. And in the bottom right, you're seeing a radially split BB5, or what's often referred to as a barrel pump. Now, we won't get into too much detail of these because we could spend an hour talking about them, but you have inline, you have back-to-back, you have single volute, you have double volute, you have fixed or VFD speed applications. All those have their place within this section. We're just talking at a very high level about some of the advantages and restrictions. Now, firstly, these can be very high efficiency if they are operating at BEP. And that it applies whether it's a volute or diffuser, BB3 or BB5. There are certain applications where you will not get the head any other way than going to one of these machines. And in that position, it's kind of a one-stop shop. And really, once you're much above 1,500 meters, this is where you end up, and this is the route you end up going down. The challenges, as we mentioned right at the start, this is the single most expensive way to do it. And we see both in our own internal install lists and when we're on sites, these are selected when they're not always needed. And that is a very, very high cost penalty to pay when there are cheaper solutions on the market. To give a very, very rough idea of where the BEP cutover is, about 60 meters cubed an hour. Much below that, you're not really able to select one of these and have them run sustainably. As we've got a little graphic up there, I'll just very briefly walk through. Right, and what we're trying to highlight here, irrespective of where the flow is, your best efficiency point is here, which is where the pump would be operating at its optimal point. And that is lowest vibration, lowest radial loads into the bearing. That's where the pump vendor has designed that machine to run. Now, it's perfectly acceptable to run further back on curve towards closed valve within this green window. There is no issue with doing that. The risk that can happen on these kind of applications is you can end up pushing them back beyond the allowable operating range, which is indicated in amber, and all the way back towards minimum stable flow. So when we're trying to do very, very low flows with this type of machine, there's a real risk that we run into this window. And this window in red below the minimum stable flow is where you end up with very high vibrations, which will lead to premature seal and bearing failures. There are further restrictions within that where you get below the minimal thermal flow, which is even much more severe as an operating condition. But the way that we get around this is pump vendors will specify a minimum continuous stable flow. And if you ever drop below that, you will need to recycle. And we can talk about why that's such a downside later, but basically it's efficiency and power loss. And you end up where you have a pump curve that you're evaluating that can look quite good, but when it's actually installed as part of your system, you're wasting considerable energy recycling back to suction. And with that, I'll hand over to Steve to talk through some of the other designs on the market.
So a much more typical design that you would see for the high head, low flow applications would be the high speed OH6 design. It's a single stage with an integral gear. Typically, it's going to operate in excess of 10,000 RPM, and in some cases up to 20,000 RPM or slightly higher. One of the big advantages is that it has a very small footprint in primarily in almost always in a vertical arrangement. You've got a low, well, the OH6 would always be vertical, so that it's a low capex cost compared to the multi-stage units. One of the challenges when we start to look at the OH6 design is a very limited operating window where the pump must be maintained and very close to the design parameters so that to avoid upset conditions. Frequently, the OH6 is going to use an inducer that has been selected and designed for the application specifically. You get an additional complexity to overhaul the pump in the vertical configuration, and that especially comes about when we start to discuss the sealing challenges. You've got a high-speed mechanical seal that's separating the backside of the impeller from the gearbox, and once that there is a leak through that that seal area, then whatever you're pumping is going to go into the gearbox, and that's when you would be forced to do either a gearbox replacement or a gearbox exchange program, or in some cases maybe an entirely new pump. You do have very high rates of speed, and so you can see increased wear due to the high operating speeds that you would see in the OH6 design. So of the technologies that all the ones that Sam has discussed, and then the one that I just reviewed in the OH6, those are all centrifugal designs. When we look at the positive displacement, this is the only technology that we'll discuss today that is not centrifugal. This is a true positive displacement. It has the advantages of being extremely high efficiency. It can be to the other, when you compare it to the other types of pumps other than the OH6, it would be considered to be very compact because we are dealing with a positive displacement machine. Then you have, it's inherent that you're going to have pulsations. You have to be aware of dampening and the vibration that comes along with the pulsations in your system. Oftentimes there'll be a lack of familiarity with this type of design. As Sam has already mentioned, there's an abundance of centrifugal machines throughout the refinery, but when we're looking at this might be the only type of positive displacement would be much less. Oftentimes there's a hesitancy within the marketplace because of the issues that are associated with a positive displacement machine. And one of those is the lack of product containment, that there is packing along the rods to keep the lubrication there. There must be inherent to the design. There must be some leakage that's coming through. And so there's a host of issues that come with that, especially in the refinery setting. So that can become an issue. And because of the reciprocating action, then there's a high use of spare parts and typically a short mean time between failure. There is a place for the machine. They're used satisfactorily in some very high head applications, especially with very low flows. And you do get a very efficient design, but you do have to understand that there will be some issues that come along with that design when you're employing it to your application. We're going to now, Sam's going to take us through the pitot tube, and that's kind of the pitot tube pump. That's where we'll spend the rest of our session today. And I just want to remind you, if you've got any questions, then please write those down, and we'll get to an opportunity to discuss those here at the end. So just please remember that.
Okay, Steve, thank you for that. So this is where we're going to spend, as Steve mentioned, quite a while now, just talking through this type of design, mainly because we think it's more neglected, it's a little bit more unusual, and it's something that does offer a unique place. And the point that we really want to stress is this is not a solution to every low flow, high head application that's ever going to be raised. What it does provide is a unique offering to the market and some very unique advantages, as we'll talk through over the next 15 minutes or so. Just as a very high level introduction then, so this is a centrifugal unit. I recognize that this is quite an unusual looking design when you maybe come from an API or what we're calling a conventional centrifugal background. But our job over the next 15 minutes is to convince you that these are very much drop-in replacements for centrifugal units. They do come with unique advantages that you cannot get with any type of conventional pump that we've talked about previously. They are available in overhung or between bearing designs, so just as we're all used to. And as we'll talk about as well, there is direct drive and there are geared options as well for higher speed applications where we're going for higher head. So the key advantage is these pumps are designed, as we mentioned right at the start, this is not a new design we are bringing to market. We can trace the heritage back of this several decades, and the whole aim of this unit is to operate reliably at low flow, high head duties. This is not a pump that has been adapted to run there. This is its operating range. This is its window. This is what it was made to do. One of the most beneficial reasons to select these units is the amount of pumps where a data sheet is issued and the pump ends up operating at exactly that duty point is very, very, very low. And what these give you is a huge window of flexibility to say, okay, we're going to design for a set point, but if we're operating drastically away from that point, these are much more robust, much more able to operate reliably back on curve towards closed valve, past BEP, than any centrifugal option. And that's particularly exaggerated when it's up against something like Steve was running through on the high speed inducer OH6. And it's where it does put us in a truly unique position. Compared to the reciprocating units we talked about as well, being a centrifugal, there are no pulsations with this design. So again, you don't need to worry about pulsation dampeners. You don't need to worry about downstream effects of that. And it does achieve a higher pressure at lower speeds than an equivalent OH6. So you can see at the bottom, we're showing there between bearing unit, and you can see that there are obviously a couple of internal gears there. So it is at a higher than synchronous speed, but you'd be looking around the 6,000 RPM mark at the upper limit, rather than, as Steve was mentioning, into the 10, 15 plus thousand RPM that you'd be on with an OH6. The challenges that we have on this, and obviously part of the reason we're here today, this is not as well known. So I'd spent 15 years in this industry, and it's not a product I was aware of until I joined Trillium. I think there is absolutely limited market awareness. We talked about that with the reciprocating units as well, and we recognize it looks a little bit different. We recognize that it's not, you're not able to specify pitot tube on a standard API data sheet. But that doesn't mean it's not compliant with API standards. And also, if you're in a very, as we mentioned, no pump is right for every service. And for very erosive services, this can cause us a challenge with the pickup tube, as we'll explain in more detail as we look at some of the cut sections. So again, as we mentioned, this is not new technology. These are single stage equivalent designs. We mentioned the two, both overhung and between bearing, as you can see in the bottom left. And you can really see that what we've tried to highlight is the low flow, high head range that we're talking about. We've just raised with this red envelope. You can see the whole Roto-Jet performance in blue and where that unit operates. This is what this pump was made to do, and you can kind of get a feel for the overall range it can cover. So again, once you are past the 170 cubic meters, this isn't the correct solution. And if you have a particularly erosive service, this isn't the solution. But within those constraints, we think there's a huge amount of applications that these could be used for, and they're definitely an underutilized design from our range. And with that, I'll hand back to Steve.
Okay, Sam, we're going to have a very short digital animation that will take us through the internal workings of a Roto-Jet pump. This is our between bearing model that we call the ROFT, and we'll see coming in from the suction end, we'll pass through API 682 mechanical seal, and the dots would indicate the fluid flow into our rotor cover that has vanes cast in those covers that are going to increase the velocity of the liquid. We're going to develop a velocity head, which is about 1/2 of the overall head that the pump will produce. Now, the centrifugal forces of the rotating case are going to cause this high velocity liquid to turn at the same speed that the case is rotating. And so the high velocity liquid will impact the always stationary pitot tube, and that taking developing the rest of the head, having the pickup tube act as a very efficient diffuser. Then it would pass through the 682 on the mechanical seal on the discharge side and discharge out into the system. So it may sound, we'll have a few diagrams and a little bit more to talk through, but it may sound a little bit confusing, but we are rotating the case of the pump around a pickup tube that is always stationary. And that's how we're getting the high energy fluid and directing it into your system. So when we look at the Roto-Jet pump as an OH6 alternative and look at applications that we typically see in refineries for a high head, low flow pumps, then you'll see everything from caustic processing, amine treating, gas sweetening, to offshore applications, reactor feed, depropanizer, deethanizer applications. So anything boiler feed water. So anything from water to low density fluids, then using a Roto-Jet pump is a great alternative. The maximum flows are typically going to be just over 100 cubic meters per hour. We have a maximum head of 1,600 meters. The maximum suction pressure is 21 bar. Without making any modifications, the maximum temperature of the pump is 120 degrees C. Then if we add some flush and some cooling, we can go to 290 degrees C. And as Sam mentions, we're typically going to be in the 4,000 to the 5,500 RPM range, and with some applications going up to 6,500 as a maximum, typically with 400 horsepower limit. We have over 20,000 pitot tube pumps have been supplied globally by Trillium. So the Roto-Jet has been used all over the world in a variety of applications, from some of the most complex applications that you can find to very simple applications.
Perfect. Thank you, Steve. So just to give a very, very quick recap, I realize the animated video maybe does a better job of this, but just to give everyone a little bit longer to have an overview of the design. So again, just recapping what we saw in the video. So from the suction point, fluid feeds down this side. Steve mentioned the seals are API 682 cartridge seals. So there is nothing out the ordinary compared to a normal centrifugal pump that you'd be seeing there. Again, ball bearing design. You can see the ring oil ring for lubrication, and the oil reservoir that you can see in amber, which lubricates both the oil ring and the gears to drive splash lubrication that way. And then fluid is passing into the rotor case and then flung to the outside through the diffuser, where it's then picked up at this point through the pitot tube. What you're seeing here, you can see there's what we'd call a double design, because it's picking up at top dead center at 12 o'clock and at bottom dead center at 6. And then fluid is channeled, recovering head all the way through this. So this passageway and the diffusion hydraulics within here are critical to the performance. And this is why when we mentioned for very abrasive surfaces, this area can corrode. But again, we're talking about abrasive, not corrosive surfaces for that. And then the fluid will continue down, and then it will come to the discharge nozzle. And then from that point on, it's into the rest of the process for the system. So again, I'm not going to spend too many time going through the features, other than to stress everything within the flanges is a standard component from our range. These are not bespoke units. This is a designed and existing range that we have. We can offer them to suit a wide window, because we can change the diameter of this pickup tube here. We can change whether it's single or double. We can change the speed they're running at. And that gives us a huge amount of flexibility for hydraulic coverage with fewer mechanical designs. And that obviously opens up more options on site should things change. But as Steve's going to mention in a lot more detail later, the unit is very robust and it's designed to almost operate away from duty conditions. Again, nothing out the ordinary in terms of the gearbox case. It's cast steel, and that's where you'll see some of the temperature limits reflecting that. We've talked around the output rotating assembly. And again, just a very, very quick recap. As you'd expect, the powers are not too significant, of around 300 kilowatts. That would apply to any of the pumps we've talked about, really, with the exception of maybe the multi-stage BB3s and 5s, where you're going for those slightly higher heads. And we mentioned the minimum operating temperatures based on case material. And Steve's talked about the upper limit. We declare in 120 degrees C there, but as mentioned, we can extend that if needed with a flush.
So the key advantages that we have, and we'll see this just a little bit later on in a little more detail, but just as a reminder, the Roto-Jet pump is able to operate across the entire performance curve from a shutoff condition to beyond the best efficiency point of the pump. It's a centrifugal design, so it has very stable operation. It's easy to maintain with easy access to the mechanical seals, smooth pulsation-free flow. It's basically a simple design with only two basic working parts, with a rotating element and a pickup tube. It's very flexible. We're able to change the capacity and the best efficiency point of a pump by changing out standard pickup tube sizes. The opening of the pickup tube is going to determine where the best efficiency point is for the pump. The mechanical seals are only sealing against suction pressure. We're never having to seal against the discharge pressure, so we don't have to worry about trying to balance the forces of a high pressure discharge in a mechanical seal. The mechanical seals are isolated from the bearing pedestals, so we don't have to worry about the contamination, and we have no exceptions to API 610. So while the pump is not included in API 610 as a designation yet, it is designed to the standard and we take no exceptions. So when we look at the Roto-Jet pump, and one of the key advantages that we talk about is the performance and the MPSH. When we look at the OH6 design and a high-speed centrifugal pumps, oftentimes the way they're able to meet the MPSH requirements of an application, especially with the lower density fluids, is by the use of an inducer. And so you can see the MPSH of the inducer, and it gives us a very curved shape that is that's quite apparent. And then it gives us the inducer operating range, where the inducer has been tuned and designed to allow the pump to operate. So if you move away from the range where the inducer has been designed, then you start to see a significant increase in the amount of NPSH that's required. And that can throw us into an immediate upset condition when we're using the OH6 design. When we look at the Roto-Jet, the ROFT, the representation of the MPSH required curve that's shown, it's a sloping line with a gentle slope, and we're able to have enough, the requirement is below that's what's available. So we have an adequate margin between the requirement and the available NPSH, and it's going to be relatively constant throughout the entire operating range of the pump, which gives us the opportunity to have a more robust design. And this is really the key advantage of the Roto-Jet pump. And I was alluding to this when I was talking about the stable operation with specifically this slide. All centrifugal pumps are designed to minimize the radial load at a given design condition. And that given design condition is typically the BEP, the best efficiency point, where the pump has been designed to operate. So the hydraulic engineer has given a flow and a head, and using that information, they will go and design an impeller or select an impeller design that will be the best, that will allow them to hit those parameters, and then design a case or a volute where the pump is going to house the impeller. And in selecting that impeller and selecting the matching volute, they're able to balance the forces at this best efficiency point, so you have a smooth running machine with low vibration. As you move away from this best efficiency point, it causes the radial load to increase dramatically. if we're going, especially as you go back towards shutoff, you can see it becomes even an issue more quickly. But anytime you move away, as you move away from the best efficiency point, you start to see an increase in the radial load. Same thing is occurring on an OH6, which is just a high-speed centrifugal pump. As you move away from the BEP, then you're going to be in a situation where you're going to have increased radial load. And the problem with the increased radial load is you no longer have a balance of forces on your rotating element. And so you get to a situation which can lead to shaft deflection. And the shaft deflection is what can lead to bearing failure and seal failure, which is the weakest link of the centrifugal design is the mechanical seal. And as you start to have shaft deflection, then you start to have a leak. And then as you start to have the seal leak, then you start to become concerned with contamination to the bearing and the rotating element. And we're able to, you can see on the Roto-Jet pump is that we have a constant radial load regardless of the flow rate. So we're able to operate at near shutoff conditions out to beyond 120% of BEP without having any change into the radial load that the pump is going to see. So that gives us a very robust design. And so that makes the Roto-Jet type pump the pump of choice when you're dealing with applications where you may have either varying flow rates or where you have processes that are especially difficult to control and you're not always able to operate at a set design condition. So with the Roto-Jet ROFT, it is an API compliant pump. We do have to have the API 682 mechanical seals. We use the size 8 or the 90 millimeter seals. We have standard designs available from John Crane and FlowServe. We've also worked with other seal manufacturers, and of course, API 682 flush plans that are available to go along with the seals. A reminder that the seals are only exposed to the suction pressure and there's no shimming that's required to set the mechanical seal. So it's a very easy to maintain and access the mechanical seals of the pump without disturbing the rotating element.
Perfect, thank you. So one of the things we want to very quickly mention was a case study. So this is a case study that wasn't done by ourselves. It wasn't done by Trillium. It was actually done by Saudi Aramco, as you can see, and it's available online, and we can share the link if it's of interest with anyone. What we are very clearly not trying to do is say that Roto-Jet is always a better option than an OH6. We're trying to stress that they all have their place. We're just trying to give an example of where an OH6 has been installed and potentially there's been a change to the design condition. The duty condition has moved slightly. Some of the knock-on impacts that can have. An OH6 operating at its duty condition will be a perfectly viable solution. It's just that is very rare where you have a process that is exactly as designed and there's never an upset window where you're potentially operating, as we were talking about on this slide, away from BEP and you're running back against higher radial loads, or you're running back on curve and you're increasing your vibration into the system. So just to run through this case study then, it was So it was a conventional OH6 installation with an inducer. These pumps were running in the teens, so I think it's around 14,000 RPM. The units were experiencing high vibration as soon as they were put in, which obviously suggests that they were operating outside their performance window, because there's nothing to suggest that the units were faulty when they were dispatched from the facility. The 4 pumps were on 2 services, so very common refinery services, transfer and wash water. And the failures, as you will see, were mostly gearbox and seal. And that's one of the big advantages that you get away with on the OH6. When you move away from an OH6, you've simply got fewer components to deal with, fewer things to seal. Access to seals is much, much easier. And the big thing to note here was 2 of these failures were catastrophic. So the units couldn't be recovered. They had to be sent back and completely almost replaced and completely overhauled. So what ended up happening was the end user replaced these. and we were ultimately switched out with Roto-Jet machines. And those pumps have been in and have operated reliably. And because they moved away from this problematic vibration window, the issues subsided. And it's purely around making sure that the pump you have is running at its specified duty. Or if you aren't going to be operating at that specified duty, making sure that you have a pump that's robust enough to operate in a flexible window. These, again, we mentioned at the very start of this, these pumps are relatively low cost. And as a result, they maybe don't get the scrutiny of other selections within a site. This warranty issue, and it's all documented in this paper that, again, is not a Trillium paper, was almost $500,000, and that way exceeds the cost of replacing that with Roto-Jet machines significantly. And it's just one case study of many we could highlight where we've been able to perform those switch outs and then have reliable operation for the customer going forward. Okay, so with that, we'll just do a recap. We're just about on time to give 15 minutes of questions to everyone. I can see that a couple have been entered already, and thank you very much for that. So this is the last slide that we'll present before we give you time to ask us anything you'd like. And again, we just want to recap, there is a huge amount of choice. This is a very, very difficult window to select a pump for and to write a specification, because there are so many options, from the conventional OH2, the low flow OH2, the high speed OH6 with gear, the multi-stage BB3s, 4s, 5s, and before you even get onto, you know, PD pumps, reciprocating pumps, and we touched on those as one pump, when really there are so many subsets within reciprocating that we could have talked about. And then the Roto-Jet range, so for pitot tube designs, where we've obviously spent a lot of time focusing on here. Cannot stress enough, there is no one type that's the best solution. And I would also say there is no one pump vendor that is always the best solution. No one has a full range of pitot design, conventional designs, reciprocating, and OH6. There isn't a pump vendor out there. Now, people have various pockets of that. We feel we have a very strong offering. I'm sure many of our rivals do as well. But what we have that's particularly unique is this Roto-Jet machine. That we feel we need to do more of a job of explaining and getting in front of customers and end users, and making people aware that this alternative is there. And again, the key considerations of which unit to pick are around capital and life cycle cost. You know, if this is purely a capital cost of which is the cheapest unit, it is going to drive you to a suboptimal solution. But the cheapest unit isn't necessarily the worst. And if it's a consistent process, you can get away with the lower cost options. It's where you need more system flexibility that we need to look for more robust engineered solutions, such as the Roto-Jet, or such as maybe moving away from a high speed geared single stage unit onto more stages at lower speed. That would be a more robust way of operating. But again, that does come with a cost penalty. There's no two ways about it, particularly on the multi-stage machine. Again, we've stressed before, no one pump manufacturer has every option, but the big piece we would mention is check overall pump efficiencies. You know, recirculation has a huge impact on this, and very often the curves that are evaluated are a pure pump curve in isolation and not a system curve. And then finally, the bit that we're trying to stress, and really why we've done this webinar, is just to say it's worth giving consideration. You know, we recognize it can be a confusing area to operate within. We just want to open the door to discussions. And obviously we're here to help guide and support. And from any data sheet, we can very quickly advise if that's something that would be a good fit for a pitot type design, or if it's better placed on either one of our other products from our range, or even one of our competitor options. Steve, is there anything you want to add to the recap?
No, I think it's a very good job, Sam, taking us back through what we've gone over today. Certainly want to leave plenty of time for questions, and not to and to be aware, help people be aware that there is an alternative to some of the more traditional pumps. And while it may be new to some of those that are with us today, it's certainly not a new design. It's for over 5 decades now. Roto-Jet pumps have been used, And so it's nobody is going to be the first person to use. Nobody on this call is going to be the first person to use a Roto-Jet pump.
So the first question we've got, so since this is a foot mounted pump, how does this pump compensate for thermal expansion for high temperature applications above 150? So I'll take that one, Steve, and then we'll move on to the second part of the question.
Sorry. We do have to be aware of doing a hot alignment when it's necessary. So that would, I'm assuming that would be 150 degrees C that we're talking about. And so that would be a necessary application or a necessary requirement there. So we would do the hot alignment to compensate for any thermal expansion that we're going to see in the carbon steel bearing frame. The second part of that question I see is, how easy is it to change the oil in the oil reservoir of the pump? There is a drain on the side of the pump, and it's very easy. Is at, of course, the lowest part of the pump, so it's easy to get the oil to drain out. It's not an issue. As far as the frequency of the requirement to change the oil under most applications, where the temperature is below the 150 degrees C range, say, then we would be looking at a 6-month interval, unless there was some particular reason where we were seeing a lot of increased temperature or something that was going to cause the oil to break down more frequently. The oil changes would have to be done. So, but typically once every 6 months, and it's pretty easy to do, not difficult.
Okay, and then we've got question 3, any minimum suction or discharge straight length requirement? So how many times a pipe length diameter do we recommend?
We don't, there's some rule of thumb for piping, and we don't have a huge requirement on any piping requirement on piping diameters. Certainly it would be nice if we could have a 10 diameter, but we know that that's not always the case. We have just coming out of our pump, we know that we have an elbow on the discharge side. So it's just there's some nice things that we don't want a lot of restrictions. The bigger thing that we would be concerned with on the piping side of the pump would be any fast acting valves that would be on the discharge side. If we had a very fast acting valve on downstream of the pump, and that is a long distance, and by long distance, when now I'm starting to talk about where we're maybe 20 meters or further down the line, where we have certainly it would probably 12 meters down the line. If we had a fast acting valve, we would be concerned about a water hammer effect of sending a column of fluid back into the pump very quickly. And so those would be the concerns. We'd be more concerned with that. But of course, any good piping practices are always appreciated by any centrifugal design.
And then we've got an anonymous question. Who are the strongest competitors of Roto-Jet, and what are the advantages of Roto-Jet over competitors?
I would say the strongest competitor of Roto-Jet is going to be the OH6 design. And so that would be by far the strongest competitor to Roto-Jet. I'm not exactly sure if that was the question. If the question is who are the competitors that are making pitot tube type designs that are more along the lines of Roto-Jet, then there's not too many people that are making this pump. There is a design out there that's available, but I believe, I'm not certain, but I believe we're the only company that is making between bearings fully compliant pitot tube type pump in the world. So that would be, so come to us. So if you want the pitot tube type design.
And then we've had a question. sorry, Steve, are you gonna?
No, that's fine.
Are these Roto-Jet pumps to be counting API in the future? Obviously, from our side, that would be a huge positive and something that we potentially should work at doing. There are no, it's not about to imminently happen, is what I tell you. And I think given the pace that these API standards move at, that could be something for quite a few years in the future. But we recognize that would significantly help us from an awareness point of view, and from making it feel a much more conventional option for our customers as well.
It was quite an endeavor to get the 12th edition out, and in the 13th edition, my understanding is only supposed to, when it starts, is only supposed to be kind of a cleanup, and then it would actually be 14th. But really, my understanding is to be included in the API 610 standard is not driven by the pump manufacturer, but it's driven by the users. So it would be up to the users, the people that perhaps that are on this in participating in this webinar, or some of the other users that have Roto-Jet pumps, to give us the opportunity to be included in the standard as we go forward.
Perfect. And then John sent a couple of questions through mentioning we have a centrifugal pump requirement for a demo unit for a methanol and gasoline application. What we'll do, John, is we'll get your email address and we'll reach out separately, and we'll be able to advise more. We'd obviously need to know a little bit more in terms of duty and conditions to be able to answer that question. But we'll reach out. If you've registered with your email address, we'll be able to get in touch with you. If you haven't registered with your email address, you can contact either myself or Steve on LinkedIn and pass your details through that way, and we can get back to you.
And I certainly, that's great, Sam. Thank you for that. And I just, one of the thing in John's questions, there was a comment about very low flows, and we didn't really go over this at all during the presentation. But while this is a low flow, high head pump, it should not be confused with the metering type pump design. So occasionally people are they're coming to us where they want to do half a cubic meter per hour application or less, and because they're really looking for a metering type design. So we wouldn't be there, but we're in the more typical range where we're talking kind of in the minimum of 3 or 4 cubic meters per hour. So if very low is in that range or above, then yes, we could have something. If we're talking less than 1 cubic meter per hour, then that's probably not going to be a good application for a pitot tube type pump.
Okay, thank you for that, Steve. I think that takes us to the end of our open questions. Unless there's anyone got anything else in the 5 minutes we have left, I want to stay respectful of everyone's time. Other than that, I really appreciate everyone's engagement. I appreciate everyone joining and allowing us the time to walk you through this webinar. And obviously, I would stress any questions, whether it's in general, whether it's specific to Roto-Jet. You have our details. Please do reach out at any point. You know, our job is to make your lives easier, and if we can help guide or support in any way, that's literally what we are here to do.
Yes, I agree completely. Thank you, everybody, for giving up an hour of your day and spending this time with us. It's certainly appreciated. One of the things I love to do is talk about Roto-Jet pumps. So thank you for giving me that opportunity.